So in this mini tutorial we're going to think about how buffer solutions work. We see in chapter 17 how a buffer solution can either be made of a weak acid and a salt of its conjugate base, or a weak base and a salt of its conjugate acid. And in this mini tutorial we're going to focus on a weak acid and a salt of its conjugate base as the basis of a buffer solution. So we've got ethanoic acid here, a weak acid, and then its conjugate base, ethanoate ion. And we need the acid present to react with any added base, and a base present to react with any added acid, and that's how we want to keep the pH the same. And the weak acid and its conjugate base need to be present in roughly equal amounts. And this presents a first problem, because if we were just to have the weak acid present, we would see this happening. So we have the weak acid, ethanoic acid, like this in solution. Because it's a weak acid, ethanoic acid doesn't dissociate very much in water at all, so we see a reaction that lies very heavily to the left. And as a consequence of this, there would actually be very little of the ethanoate ion present in solution. There would be hardly any of that, and not enough to make the solution work as a buffer solution. So instead we add the salt of the conjugate base. So let's imagine we've got the sodium salt. And when we put the sodium salt in solution, it dissociates very extensively to form the ethanoate ion in equal solution, and then the sodium ion, which is just a spectator. We don't really need to care about it as far as the buffer solution is concerned. What we do see then is plenty more of the conjugate base being formed, which tops up the conjugate base that would be present from the very limited dissociation of our weak acid, ethanoic acid. So what happens then if we've got this buffer solution set up and we add an acid to it? So let's imagine we add just a general acid, which we're going to use HA to represent acid. We add it to the solution, and this is then going to dissociate like this. And this is the acid that we're worried about. That's what we need to get rid of to keep the pH the same. So what happens is, when we add this to the buffer solution, our weak conjugate base comes into play. So our ethanoate ion, CH3CO-, reacts with this extra acid that's just been added, HTO+, to form its conjugates. We've got the ethanoic acid being formed and water. So what we see is the equilibrium reaction at the top being pushed from right to left to compensate for the added acid. Now what would happen if we added a base? So again, a general base reacts in solution like this. It goes to BH plus OH minus. And in this case, it's the OH minus we need to worry about. We need to be getting rid of that. And when we add a base to a buffer solution, we see a neutralization reaction occurring. So basically, our weak acid, in this case ethanoic acid, reacts with base to form a salt and water. And that's the general form of a neutralization reaction. Acid plus base equals salt plus water. So what you're actually seeing here is our spectator sodium ion forming the salt with the ethanoate ion. So in effect, in this instance, when we're adding the base, our reaction at the top here is being pushed from left to right to compensate for the added base. So we can see how a buffer solution, both the weak acid and its conjugate base, are working if you add either an acid or a base to the solution to maintain the pH, so that neither acid or base concentration in the solution effectively increases or decreases at all.